Today we tested our BPM-5 engine. It was the BPM-5 number 3 that was in a test stand, and it's the engine that's actually gonna fly on Nexo 2 this summer. The goal for today was to map out the dependency between OF ratio and the combustion chamber pressure. So we've implemented a new algorithm that will allow us to ramp up the pressure during the burn. So during the burn, we'll actually change the pressure in the propellant feed tanks via the dynamic pressure regulation system that we have upgraded. As you can see, the whole test setup is pretty big, and now pad leader Jakob will tell you more about the test stand itself.
So welcome to this slightly foggy day here at Copenhagen Suborbitals. February 4th, 2017, and we're just in a little intermezzo here in between, having different parts for the test of today having been brought down here to the test stand. So there is a little bit of a chance for me to show you again how this test stand is put together. So the test stand is split in two. There is a bulkhead in the middle of the test stand which separates the engine on the far side from here, and then we have all the electronics, the propellant tanks, pressure bottles, all the mechanics are on this side of the test stand. So I'll just walk it over with you and just show you which is which. So we'll start out with these two tanks, which look fairly identical. The one here on the right, that's the fuel tank, and the one on the left is our liquid oxygen tank. Now it's easy to see it's the liquid oxygen tank because it has a lot extra hardware on the top. Liquid oxygen is cryogenic, about a minus 180-85 degrees Celsius. So it has the capacity to cool down everything around it. And it's really annoying. It's supposedly easy, but everything around it in the vicinity or mounted on the tank itself, the temperature plummets, and it can disturb electronics, it can make seals leak, it has all sorts of potential hazards with it. So the fuel tank, the one here on the right. We have our fuel in it. In our case, it's ethanol in various dilutions with water, but usually 75% ethanol, 25% water. It sounds odd, but it just has some very nice combustion traits. We fill it from the bottom through a sideline we have down here. We do it from a small pressurized canister that is just a slight overpressure, and it just gently squeezes the fuel into the tank. Now, on the top of the tank, we have a number of sensors, but also a number of extra spare ports. We are very fond of these tri-clamp fittings, which also probably known as diary fittings. The sensor port is currently, it holds one sensor, which is a little green temperature sensor you can see on top. That's for measuring the temperature of the gas bubble above the ethanol. It's not that interesting in the case of the fuel, but when we get to the liquid oxygen side, it has quite an important relevant role here. Now, the sensor port is also where we pressurize the fuel tank, so that we have the possibility of simply forcing the fuel out the bottom and into the engine. Now, the most elaborate thing we have on top of this tank here is the one on the left. It's also something we usually refer to as a Christmas tree. It is a unit which contains as many different standardized objects that we need for making a safe test tank. In our case here, we have a manual pressure gauge that is in case we lose all power on the test stand. An electronic gauge wouldn't be of any use to us, so we have a manual one for backup. You can always go look at it with your eyeball, or you can put a camera in front of it. Of course, then the electronic pressure transducer, so that we can, in mission control, we can read the pressure of the tank. Now, the two last parts, one is a safety device, also known as a burst disc system. It's a calibrated system with a very thin disc of aluminum with very known properties. And it has been designed in such a way that this aluminum is stretched to the border, really, by the pressure inside the tank, and at a very well-defined overpressure or safety pressure, that disc simply ruptures and just bleeds the pressure of the tank. Now, if you have a let's call it a freak event where you lose electrical power on the test stand, and you can't, and you're in the middle of pressurization process and you can't stop it, in theory you would simply just overpressure your propellant tank to the point where it bursts, and it's not a good ending in any way. So this very simple burst disc system will just rupture and bleed the tank much faster than it could ever be filled in case of an overpressure event. So it's the last line of defense, and no, we always have these. Now the last part of it is the vent system. With the ethanol, it's hardly ever used because the ethanol is just a docile liquid at room temperature. Again, it's more relevant on the oxygen side, where the oxygen evaporates and builds up a pressure inside the tank by itself. So that's more or less all of the mechanical and electronics used in the fuel side propellant tank. Now onto our oxidizer tank. Again, a stainless steel tank, very rugged. And insulated, this time with more than a few layers of mineral wool. Liquid oxygen, cryogenic, extremely cold, evaporates at room temperature, so we simply need to keep the heat out of the tank. Again, we fill it and we drain it from the bottom through one port down there, and then we again have a number or an array of sensors and mechanics on top of the tank. In this case, we have some temperature sensors, 8 of them, at different levels down in the tank, and it was just an experiment to see if we could measure liquid oxygen level inside the tank by use of just a simple thermocouple or array of thermocouples. It actually works, but we're not really using it. Today we're using a much more elaborate piece of electronics, which is a capacitive dipstick. Basically it's a contactless level sensor that can actually measure these cryogenic fluids. It's very, very difficult. So a specialized system is needed for that. On the right, again, we have a Christmas tree with the standard options of a manual pressure gauge, an electronic pressure transducer, the burst disc system, and in this case, the very much important the vent valve. The liquid oxygen evaporates inside the tank. It builds up pressure by itself, and it will rupture of course it will rupture the burst disc, but it has the potential to rupture a propellant tank like this. The pressure becomes extremely high. So we have an electronic system that simply just lets out a little excess gaseous oxygen whenever the pressure builds up too high.
As the test stand is almost ready, Flight Director of the day, Thomas Pedersen, gives a small briefing to the rest of the crew to see if there's any potential issues anywhere in the system. So when you guys are done, we'll commence with the sort of a pre-flight checklist, checking out the test stand. So we will do the usual valve check, pressurization check, and after that's completed, then we'll start loading fuel and locks, and then we're ready for the first shot. So with a bit of luck, then we're still up for the first shot at around 2 o'clock, maybe slightly past 2 o'clock. Right, so the first test, we're aiming for an OF ratio of 1.3, and we're ramping up the pressure, chamber pressure, from about 12 bar to about 16 bars. So that's test number 1. Then we'll see how it goes, and then we'll evaluate on that. And so I have the numbers ready for the next test, but let's just evaluate on the first test how it goes before we finalize the numbers for the second test. Right. So unless there's anybody who has something else, then I think that you guys should finish.
Pat.
Stand by for step 13. We are depressurizing.
Noted, standing by.
Here the pad crew is still setting up the test stand. They are currently connecting the locks below between the engine and the tank. There's actually a lot of stuff to check out on the test stand. It consists of several valves, both between the tanks and the engine, but also between the high pressure system and the propellant tanks. And we spent quite a lot of time making sure that all valves are operating correctly and that all the feed lines are leak tight. The high pressure system operates in excess of 200 bars, so naturally it's very important to ensure that it's absolutely tight.
The lock tank to 1 bar as well, over. This is Pat, please proceed. Lock tank is at 1.
At this point we're conducting a valve check, to see that the valves on the propellant tanks are operating correctly. So we're actually pressurizing the tanks to 1 bar, and then we open the vent valve to ensure that it's operating correctly. And after that we'll open the main propellant valves to ensure that they can also operate correctly.
Right, you are go for loading liquid oxygen. We are aiming at 50 liters, over.
Filling the liquid oxygen tank is a delicate operation. And if you saw our Nexus 1 flight, you noticed that we had a few issues with this. So on today's test, we have implemented a new LOX level sensing system. It consists of a capacitive stick, which sits in the LOX tank, and by capacity, it's able to measure the level of liquid oxygen in the tank. As you can see on the display here, it reads out in liters, quite accurately, how much liquid oxygen is currently in the tank. As we're filling the tank, you can see that a lot of the liquid oxygen evaporates and is vented out through a vent valve.
Yeah, lock this flight. I would like to correct the injected locks.
Initially, when we fill the liquid oxygen tank, a substantial amount of the liquid oxygen actually just evaporates and forms gaseous oxygen, and that's what you see escaping the vent valve here. As Copenhagen Suborbitals is a crowdfunded project, we always invite our supporters to come and take part in our static tests.
Go, Caro.
As we're getting ready for today's first test, we run into a problem. We don't have a connection to the igniter inside the rocket engine, so we have to send in the electronics people to debug the situation. It turns out that one of the relays that triggers the igniter in the engine is actually faulty. But luckily we actually had a spare relay, so we just replaced a few wires and then we were good to go again.
Go. Thank you. Pat, can you confirm test stand is clear? This is Pat, test stand is clear. Alright, everybody, this is a flight. Pressurization is imminent. This is a DVR burn.
Test preparations follow a strict checklist to make sure that everything happens in the right order and sequence. When flight director thinks that everything is ready, he performs a go-no-go call where all team members confirm if they are go or no-go for test.
Go, no go, Quad Alpha. Quad Alpha, go. Booster. Booster, go. Water. Water test down, go. Water, fire suppression, go.
Photo.
Photo, go.
Pyro.
Go.
What's got? Data?
Go.
Yeah. And data's go. Okay, we have green board step 67.
Alright, we will commence pressurization.
Good.
Alright, we are pressurizing the fuel tank.
When all systems are ready, we use the DPR system to pressurize the propellant tanks. And when they're fully pressurized, we initiate the 30-second auto-sequence start procedure.
17 bar. We will commence 30-second auto-sequence start in 3, 2, 1, go.
From here on, the sequencer automatically counts down to -2 seconds, where it ignites the igniter inside the engine. At 0 seconds, the main propellant valves open to their pre-stage position. After an additional 0.5 seconds, the valves open to their fully open position and the engine is running in main stage.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition.
som om den brændte ud.
Det kan godt være, at det var den, der triggede den. Jeg kiggede ikke lige efter tiden.
Alright.
Det ser ud som om vi har lukket. Jeg kan ikke se flammer.
Godt. Du kan depressurize. After the engine has been running, the fuel line is purged with nitrogen and a big fireball comes out of the engine. After that, we depressurize the 2 propellant tanks such that the booster crew can approach the test stand and make it safe.
Alright, booster, you may approach. We are pressureless.
Booster approaches the test stand and observes that there's no visible damage to the test stand. Make sure that there's no fire or that the engine looks healthy. After that, the photo guys approach and they turn off their cameras and store the pictures. We usually have quite a lot of cameras on the test stand. I think the max we have ever had was up to 19 cameras. So the photo guys are usually pretty busy. As Copenhagen Suborbitals is a crowdfunded project, we always invite supporters to come and see our tests. We usually also invite them to get really close to the engine. And
It is possible to actually touch the rocket engine. You must only touch it on the upper side. You must only use flat hand and be careful if it's still hot. But you can tell everyone at home, I touched the rocket engine.
in the following, we have footage from the 3 remaining tests. Shortly, the tests were very, very successful. We got a lot of good data, and this particular engine had only been running once before. On this day, it ran 4 times of 30 seconds, in total 120 seconds of runtime, and it exerted 600 kilonewton seconds of thrust. Thus, with this very successful test, we are now quite sure that the Nexus 2 flight engine is ready to do its duties. Now, it's a bit of optimization of the DPR algorithm. This test was a milestone in preparation of the Nexus 2 flight, which is scheduled for this summer.